Hi everybody. So the purpose of this video is to go over the SPSS output that Kati and I will be sending to you. While you have your data collected, a lot of you just probably have it in SPSS. And of course you don't have access to that anymore. So we'll open up the data and doing the analysis and then sending you data tables that look similar to this, or output that looks similar to these tables in terms of configuration. So the purpose of this video is just to go through descriptive statistics, correlation tables, and t-test tables, and just kind of learn how to interpret the output so we can later extract this information and actually use it to generate our plots in Excel and our tables in Excel, as well as for our results section, our APA style reporting of the information. We also there's information here that we need to extract and use. So I have fabricated all of these data for the purpose of this tutorial. I have 5 variables total. I have kind of like my IV and DV I'm using, which is going to be height and weight. And I also have a third continuous variable of age. So all of my continuous are in these columns. And then the two factors or categorical variables that are broken up into 2 levels. So they're binary, are sex, male and female, and cat status, more or less. So if you own at least one cat, you fall into the yes level of the factor. And if you do not own any cats at all, you fall into no. So up here with our continuous variables, it's go ahead and it's going to give you some information. It'll show you how many observations there are. So I made up 10 different observations that all contain, for all 10 observations, there's no missing data. So at least here for height, weight, and age, it's saying that, for the 10 observations, there's no, observations where they're missing their data for a particular variable. It makes sense to have means when you're using continuous variables. Also, I have 2 measures of dispersion. I have a standard error of the mean as well as the SD here, which you're more familiar with. The reason we're getting into standard of the mean because you will use information like that to help you with graphing. One thing I want to point out is notice that the SEM, even though they're both measures of dispersion, the SEM is always smaller than the SD. I also have here the minimum and maximum values. These are what you're going to use to create, you're creating your APA style tables. They're going to use these to create your ranges. So this is giving you, out of everyone, the true minimum, response or measure, the true maximum, and then you just put them together with a hyphen, and that'll be your range. For our nominal variables, sex and cat here, we only care about, these are frequency tables, so we only care about the frequencies. And while we have the raw frequencies here, on the left kind of here, we really, when we're reporting it in our tables, we care about the percent column. So I went ahead and did 50-50 for male versus female, just for my t-test later. It helps with the t-test. I also have, just kind of for fun, and also there's a purpose I'm doing it for the t-test later, but I have this cat status variable. Notice that this one is not 50-50, so if we look at the frequencies, more people from this random sample of 10 have cats than don't have cats. One thing I want to point out about these binary categories or factors is that, and this will become very evident when you're reporting it in your table, your APA style table, is that if you arbitrarily choose to represent the percentage of one, the reader should already know the percentage of the other, right? Because if we have 100% total and you say that 70% have cats, then it's necessarily the case that the percentage of people that don't have cats are 100 minus 70, which is 30. So just something to keep in mind when you're making your table. So these descriptive statistics are all good, but let's go ahead and get to the output of our statistical tests. So height and weight, it makes sense that there would be some positive correlation there, right? You would expect, taller people, they just have more body mass really in general, so they probably weigh a little bit more. Where smaller, people of less height would probably weigh less on average. With your correlation output, you're going to get a descriptive statistics table. We might not even send this to you just because this is not any more information really than that first descriptive statistics table. looking at the height and weight features. The thing of interest here is this correlations output. So right here's the Pearson's correlation. So that's Pearson's R correlation coefficient. And I said going into this, we would already expect that there probably would be a positive correlation. And this seems to be true because if you look at over here where it kind of looks like a matrix, if you look for both height and weight, their Pearson's R, you notice it's the same value, right? Because we're literally just comparing, height to weight and then weight to height. So it's the same thing. So you're going to have the same value. You can see that this is 0.899, which is telling us that there's a very strong positive linear correlation going on here between height and weight. So in a linear fashion, as height increases, weight increases, and as height decreases, weight decreases. So they're increasing and decreasing together, and that's what's making, or in the similar way. So that's what's making it a strong positive linear correlation. And the reason I actually know it is because I'm looking at this sig two-tailed, my significance value here. So this is the p-value. The p-value here they're approximating it as 0.000, which is a very small number. And if you remember from lecture, our kind of the universal alpha value we're using is 0.05. So if we want a significant correlation occurs when our p-value is less than the alpha value. So we want p to be less than 0.05, and this is definitely less than 0.05. So we'd report this as p is less than 0.05, and this is basically telling us that yes, it is with good probability this is true. That most of the time you're going to get this strong linear correlation, close to one, close to even, this one's close to a perfect one even, so it's very strong. And we'll see when we're plotting with our scatter plot that you can see visually that this is very evident. Also, if you, a cool thing about this is they'll also give you these asterisks here, which are a quick way to tell you that there's a significant correlation between the two features, because and they'll tell you down here that like the more asterisks you have, almost the more rigorous the alpha level they're setting. So it's just saying even if you had a more rigorous alpha level of 0.01, it would still be statistically significant. So last but not least, we have our independent two-sample t-tests. I went ahead and did two of these, one to show you another example of a significant finding, and then an example of when there's no significant difference. So for this first t-test, if we look at the group statistics here, it's actually giving you more information than that original descriptive statistics table. This is actually really valuable. In fact, you're going to use these tables when you're creating bar graphs, because what it's doing is it's taking this feature, so our dv again, right? So in the original problem, we had two continuous variables, right? We had kind of like height as our IV and seeing how it how it correlates with weight as our dv. In this particular instance, we're going to use the same dv of weight, but instead we're going to see how this continuous variable, looking at its variance, how the observations separate from each other and separate from their central tendency measure, their mean. We're going to see if this variability is influenced by our factor of sex, which would make sense. Because if you think about it, if you were to randomly sample a couple of males from, say, the U.S. population, randomly sample a couple of females from the U.S. population, we already know that there's a difference in those means. You're going to the average male is going to be heavier than the average female. So we have a pretty good there's evidence and support already of our alternative hypothesis, where this is almost more confirmatory. So if we look at the mean, so I said earlier that we have same number in each group, which is good. But right here we have the means, the SDs and the SEMs broken up by the different levels of the factor, which is cool because earlier, as I said, that weight feature we had just a single mean and SD and SEM for it, and it didn't. It included, it pulled these together. Where now we're separating them, and we're just calculating a mean and SD and SEM for these 5 that are in the male group, and then we're doing the same for the female group, so that we can have this sort of see the separation in means. And so, we've got good evidence already from the descriptives and knowing stuff about our population that we're probably going to get a significant difference. So now let's look at the actual t-test output. And so we only really care, there's a lot of information here, but the only things we really care about are this t statistic, that t calculated, our degrees of freedom, which just as a reminder is our number of observations in this case, minus the number of levels pretty much of our factor. So in this case, we just have, you can be in 2 different categories. You can be male or female. So that's 10 observations minus 2 is 8. And then here's our p-value again, right? The sig2-tailed, here's our p-value. In this case, it's not only, it's actually giving you a more exact p-value. So it's always approximating, but with this one, it's basically saying p is equal to 0.021, which is less than 0.05. So this is another significant, this is telling us there is a significant difference. We can reject the null hypothesis that there's no difference between male and female, mean weight, and we can support the alternative hypothesis that there is. So yeah, that's very valuable information. Also, here when you're reporting, you could still do the p is less than 0.05, but I would still accept something like p is equal to 0.021, because if p is equal to 0.021, then it is necessarily less than 0.05. So it's just, you can report it slightly differently. I also wanted to point out that when you're doing your bar graph, this table is going to be very important, because it's actually these means and these SEMs, these standard error of the means, that I will want you to use to plot your the actual bars of the bar graph, and then the error bars of the bar graph. So the mean, we use the means to make the bars, and we use the SEMs to make the error bars. I'm going to show you all of that in a later video using Excel, but just to point out that this is the table you're really going to look at to extract the information for creating that bar graph. So that was a significant result. What about an insignificant, or one that is not significant, rather? So that's why I did the whole kind of goofy cat variable, because one wouldn't really think that one's status as a cat owner has anything to do, or you would think it's very independent of variation in weight, right? You wouldn't think that whether or not someone has a cat means that they would be heavier or lighter than someone who doesn't. So we kind of go into this one knowing that probably there's a greater chance of our null hypothesis turning out to be true. One thing I also want to point out is that notice that unlike this, we have pretty even frequencies. Or with this, it's not even. In fact, it's kind of bad, because one group's it's pretty low, it's pretty abysmally low to have only 3 observations in one of your levels. So yeah, not the best stats here, but if we look at the means, they're pretty close. So this is pretty much, we know this is probably not going to be significant. And then lo and behold, if we look at the same region as we did before, that the T, the DF, and the sig2-tailed, if we take the absolute value, this is 0.2. T-calc is much smaller in this case than it was in our last example. It was like 2.8 something. DF would be the same. P-value in this case is going to be equal to 0.84, which is pretty high for a p-value, certainly higher than 0.05. So in this case, we have finally gotten to a scenario where we have failed to reject the null hypothesis. So it's still safe to assume that really your cat ownership status has nothing to do with whether you're going to be way more or less than someone else, given their cat status. So that's all I have for this video. I hope this was helpful. In the future, I will make 2 more videos, as already stated, and I'll see you soon.